Welcome to Ascend Code. Hey, ready to write some code that will make your future self thank you? Hit that subscribe button and let's make your coding journey as smooth as your best script. Visualizing binary heap operations can be a very helpful way to understand how these data structures work. This example demonstrates the behavior of a min-heap data structure, where the smallest element is always at the root of the tree. The min-heap is implemented using a list, and the example provides functions for inserting new elements and extracting the smallest element. The code demonstrates how a min-heap works by visually representing its structure after each operation. It shows how elements are inserted and the necessary adjustments are made to maintain the heap property. It also shows how the smallest element can be extracted while maintaining the heap structure. The visualizations help to clearly see the changes to the heap structure at each step of insertion and extraction. Import the required libraries for visualization. Use to display the graphical representation of the heap. Network X is used to create and manipulate complex networks of nodes and edges, the binary heap tree. Min-heap class defines the heap structure and contains methods for heap operations like insertion and extraction. The constructor initializes an empty heap. Self.heap will be used to store heap elements. List to store elements. This is where the heap values are kept in a way that satisfies the heap property. This function is used to visually represent the binary heap as a graph. Create a directed graph object using Network X to represent the heap structure. Directed graph because we are modeling parent-child relationships in a tree. A dictionary to store the values for each node. Key is the node index, value is the heap value. Iterate through each node in the heap list, represented by indices. Add the node to the graph with the label as the heap element value. Add edges between the parent node and its left and right children, if they exist. Add an edge from the parent to the left child. Add an edge from the parent to the right child. Set the label of the node to its value in the heap. Generate positions for nodes in a way that makes the tree appear properly arranged. Spring layout is used for more intuitive visualization. Draw the graph with the specified node positions, labels, and other visual settings. Title the plot and show it. Insert function adds a new element to the heap and maintains the heap property. Add the new value at the end of the heap list. This is always where new elements are inserted. Call the bubble up function to ensure the heap property is maintained. Visualize the heap structure after insertion to confirm its correctness. _bubble_up ensures the heap property is maintained after adding a new element. This function compares the newly added element with its parent, and moves it upwards if needed. Continue bubbling up, as long as the current index is not the root of the heap. Calculate the parent index using the formula for binary heaps. If the current node is smaller than its parent, swap them to maintain the heap property. If no swap is needed, exit the loop. We have a valid heap. Swap the current node with its parent. Update the index to the parent's index and continue the bubbling up process. Extract_min function removes the smallest element, root of the heap, and reorders the heap. If the heap is empty, there is no minimum element to extract. The root, smallest element, is at index 0 of the heap list. Move the last element in the heap to the root, and reduce the size of the heap. Call the bubble_down function to restore the heap property. _bubble_down ensures the heap property is maintained after extracting the root. This function moves the element at the root down to its correct position by comparing it with its children. Write child index in a binary heap. Check if the left child exists, and if it is smaller than the current node. Update smallest if left child is smaller. Check if the right child exists, and if it is smaller than the smallest so far. Update smallest if right child is smaller. If the smallest element is not the current element, swap them. Swap the elements. Recursively call bubble_down to continue restoring the heap. Example usage. Insert values into the heap. Each insertion will maintain the heap property. Extract the minimum value, root of the heap, which is the smallest element. The root value, 5, will be removed, and the heap property will be restored. Now run our code. That's it for today. Please like and subscribe to stay up to date with new videos.